Hey y'all, this lesson is on solving systems of inequalities. So we've already learned how to solve systems of equations, and now we're just going to extend that into inequalities. This becomes really useful in business math. So if you're going on past college algebra and you're looking at cost, revenue, and profit, you're probably going to be seeing this again. So it's very useful. As you learn this lesson, I want to encourage you to get a highlighter or maybe some matte pencils to help you with this. It can be kind of fun if you jazz it up with some color. When you're graphing linear inequalities with two variables, there's some things that I want to cover before we get into systems. So we're going to look at just a singular inequality before we get into the bulk, the meat of the lesson. So when graphing an inequality with two variables, usually x and y, you graph the line of the equation like normal, and then pay attention to the inequality to decide whether the line is dashed or solid. So in a linear inequality with one variable, we use a number line, and on the number line, we either use a closed circle or an open circle, or we did the bracket or parentheses, depending. So now instead of one variable with one number line, we have two variables, and that's where the x and y axis come into play. So when we have, oh, and then you'll shade, you have to decide where to shade. So when we have these different types of inequalities, the first type of inequalities are less than or equal to or greater than or equal to. And what I want to point out here is that these both have the equal to symbol with it. And so this is going to be a solid line. And then in the one below it, less than or greater than, we don't have equal to, so this will be a dashed or dotted. Either way, as long as it's not solid, we're good. And so let's graph one inequality just to kind of review on how to graph. This inequality is in slope-intercept form. Our slope is -3 and our intercept is 5. So I'm going to graph my line like normal. I am having trouble. It's a little slow today. Okay, hopefully I have fixed the lag in the screen share. Sorry about that. So the slope is -3 and the y-intercept is 5. We're going to graph that really quick, like normal, 5, and then we go down 3, right, 1. And then now is where it's a little bit different. I need to see if the line is dashed or solid. So I look at the inequality, and since it's less than, it's going to be a dashed line. So I'm going to draw, it's not exactly straight, but you get the point. Try to do it as straight as possible. And then we need to do our shading. So this is where your matte pencils or your highlighters will come in handy. We are shading the y values less than this line. So the y values below the line. And that is going to be all down here. And if you have just a pencil, you can do like lines, like that. That's fine, just to show that there's shading on this side. And what we're saying is all the values, all the solutions coordinates, that's what I'm trying to say. All the coordinates below the line satisfy this inequality. So I could pick any point in this region and plug it into my inequality and it would be true. So let's just try 0, 0 because that's a really easy one to try. Is 0 less than, zoom out a little bit, -3 times 0 plus 5, question mark. because I'm testing it. That's going to be 0 plus 5. Yes. So that shows that I shaded correctly. Now, if I chose a point up here, it should come out to be false. So we'll do 4, 4. Is 4 less than negative 3 times 4 plus 5? That's going to be, is 4 less than negative 12 plus 5 is negative 8? No. And that's why we're not shading up here. So if you're unsure as to where you're supposed to be shading, you can always test a point and that will tell you whether that's a good region or not. When we graph a system of inequalities, we graph both inequalities on the same coordinate plane, and where the shading overlaps is where our solutions lie. So when I say it's where our solutions lie, I mean it's where the solutions live, basically. So they are solutions that satisfy both inequalities. Can solutions live on a dashed line? What do you think? Just take a guess. And now let's think about what a dashed line is. A dashed line stands for less than or greater than, but not equal to. So since it's not equal to, that means that none of our solutions live on the line. So can solutions live on a solid line? Yes. Solid line has the equal to sign. So yes. Solutions can live on a solid line. So let's practice. Graph and state some solutions of this system of inequalities. There's several ways you can graph these two lines. You can, since they're in standard form, you can use x and y intercepts, which is really fast because these are going to divide evenly, or you can put it in slope intercept form. Either way is fine. I would probably recommend going ahead and putting it in slope intercept form because sometimes this y value is negative, and when the y value is negative, what happens to that inequality? When you divide by a negative, what happens to the inequality? It flips. So I would be very cautious about doing x and y intercepts. That can give you 2 points to help you graph the line, but to figure out your shading, you're going to have to pay attention to that last step. And let me just kind of remind you what I'm talking about. We've got this inequality here. If I were to isolate y, I would need to subtract 3x. And then this is what I'm talking about. I'm going to divide by 6 as my last step. If the 6 had been negative, then I would need to flip the inequality. So because that dividing by that negative negates the whole inequality. So just be careful of that if you're going to do x and y intercepts. Just realize that if this is negative, that sign is going to flip. But since it's positive in this case, it doesn't matter. You should get -1/2 x plus 1. So you could graph this line. A -1/2 x plus 1 goes through 1, down 1 over 2. This is a solid line. That's pretty close. That's a little better. Not great, but a little better. And I'm going to save the shading. I'll go ahead and shade because I have highlighters. I think it's easier if you have highlighters. We're shading the y values lower than, less than, or equal to this line. So that's going to be, I'm getting a little messy, but you get my point here, hopefully. It doesn't have to be perfect. We just have to show that it is below the line. And now I'm going to graph the second line On this one, I'm going to use X and Y intercepts just to show you, remind you of that. And I'm positive that I can do it because I'm not going to be dividing by a negative. So my X-intercept is 2. I'm going to do an orange dot so that I can tell the difference. And my Y-intercept is 4. Again, an orange dot. This is less than or equal to, so it's going to be a solid line like that. And we can see where they cross, but that's not necessarily what we're looking for like we did in equations. Now we're looking for the region where their solutions are the same. So if I were to shade less than or equal to this line, that's going to be here. And we're going to be able to tell where the shading overlaps, especially with highlighter. I love this about this app, or even highlighters. You can really see where those colors overlap. So here, maybe I can highlight it in blue. We'll see. Here is the region where our solutions are. See how it's much darker over there? And remember that this extends past the graph. This is just as far as on paper, this is what it looks like, and it extends indefinitely. So these are our two lines, and we shaded for both, and where the shading overlaps are the solutions to your system. So anything in this region and beyond, because it goes on, and on the lines are solutions to the system. So when I say solutions to the system, I mean that it's a solution that fits both inequalities. If the point does not prove to be true for both inequalities, then it does not work. Even though it may be true for one inequality and not the other, you cannot use it as a solution for the system. A solution for the system fits both inequalities. So I could pick any point in this region and on the lines, as long as it is in this area. Nothing up here, nothing over here, nothing here, nothing here, nothing here. None of that counts. Only the dark region and the places on the line. So I could pick 0, 0. That's a really easy one to pick. And I'm going to test it on both inequalities just to show that it's true. So in my first inequality, I'm going to actually use purple since I graphed it with purple. 0, 0. I'm going to put a question mark because I'm not sure if it's true. I'm pretty sure, but 0 plus 0 is 0. That's true. Now, that's not enough to say that that's a solution to the system. I still need to check the second inequality. So now I plug in 0 to the second inequality. I want to know if it's true. 0 plus 0 is 0. That's true. So since it fits both inequalities, 0, 0 is a solution to the system. So some examples would be 0, 0, -2, -3, 2, 0, looks like. You can list out as many as you want. I'm just trying to show, for example, where those are. You can list a whole bunch of them. There's infinitely many. We could never list them all, but there's just a few of them to kind of show you. Nothing up here is going to work. So the next one, we've got x is less than or equal to 2 and y is greater than or equal to -1. These are going to be horizontal and vertical lines because they only have the one variable. So on x is less than or equal to 2, we're going to graph that like x equals 2, which is a vertical line through 2 on the x-axis. And I used a solid line, y, because it's less than or equal to. So over here, and then don't forget to shade. throw some shade on this graph. Haha. And then it's not perfect, but it's good enough. Y is greater than or equal to -1. We're going to graph it just like y equals -1. So that is a horizontal line through -1 on the y-axis, solid. Greater than means values above, y values above the line. So I'm going to do orange, orange. My husband always makes fun of me because of the way I say orange. It's orange. There we go. And now we can see where it's darker. It's up here in the top left corner. Our two lines have basically set up 4 quadrants in addition to the original 4 quadrants of the coordinate plane. But the top left quadrant is what we're looking for. So anything in this region and on the lines will be true, or will be solutions to the system, sorry. So some solutions, you can go ahead and pause it and list some if you want to. An easy one is going to be 0, 0. That's obviously my favorite. 0, 1, 0, 2, -3, 0, -3, 1, -2, -1. It's on the line, but it's fair game because of the equal to. Even 2, 0, 2, 1. Again, whoops, that's on the line, but it's a solid line, so we're good. If either one of these lines had been dashed, then I cannot list any points on the line. So there's that. You might have some different points, and that's okay, as long as they live here and beyond, because they keep going, then you're good. All right, last one. We actually have a system of nonlinear inequalities, which is kind of fun. So the first inequality is y is greater than x squared. Now, we don't really know what x squared looks like yet because we haven't really studied it, but we can use a table of values. So anytime you don't know how to graph something, you can just default to a table of values. So I'm going to do a table of values over here on the left. I'm going to do x and y, where y is x squared. So I'm just going to pick some values for x. I'm going to pick some negative values and some positive values to give me kind of a good idea of what it's going to look like. -2, -1, 0, and 1, 2 are always pretty safe. Not always safe, but pretty safe. So -2 squared is 4, -1 squared is 1, 0, 1, 4. And basically you can see we're going 4, 1, 0, 1, 4. We're going down and dipping back up. So it's decreasing and switches to increasing. This is a U-shaped graph called a parabola. So we are going to sketch that over here. 0, 0, 1, 1, 2, 4. 3 would go to 9. Doesn't fit. It's okay. And then there's a mirror image on the other side. -1, 1, -2, 4. Now, before we draw this curve, we have to pay attention to the inequality. It says greater than x squared. So since it does not have the equal to, we're going to do a dashed curve, which is going to feel kind of weird, but just go with it. Goes up that way. And then greater than kinda is going to put us, not kind of, it is going to put us in like the cup, kind of, in the cup, you could call it a cup. So because those are the y values above the curve. These y values are greater than our curve. And then our second inequality is y is less than or equal to 5. We know how to graph y equals 5. That is a horizontal line through 5. And this is a solid line. And we got a shade. So less than 5, less than or equal to 5, is going to be above or below our line. Less than is below. So we're going to shade down here. It's kind of a big area. We get to color some more. I love when we get to color in math. Super fun. Get to in geometry a little bit more than algebra, but we get to sometimes. All right, so we can see that the overlap is inside this U-shaped graph. So we have this U-shaped graph that's kind of got a lid on it, and this region is bounded by the curve and the line. And this is definitely going to be where you see this come into play. Not necessarily these types of functions, but you're going to see this come back into play if you take business math. The first part of business math is algebra based, and you'll get into linear programming where you have 3 inequalities. You're graphing 3 linear inequalities to figure out the triangle. I can't do a triangle. A triangle where these 3 lines, there we go, 3 lines overlap, and typically speaking, your shading is going to be inside my terrible triangle, and it's bounded by the lines. And you have to use those intersections and the shaded region to come up with your solution. So, long story, not part of this course, but it is pretty cool. And that's getting into cost, revenue, and profit. This is algebra, so strictly algebra, so we don't have to talk about that necessarily, but we do have this area that is bounded by our curve and our line. And we do need to note that none of these points can be included as a solution to our system. But these points are okay. Those are good. And then everything inside is also good. So if you want to practice, pause it and write down some of the solutions that work to the system, then go ahead and try it. So hopefully you got something like, we could do 0, 1. Whoops, forgot my 1. I always forget the 1. I do the, anyway. 0, 2. I'm not being very risky here. I'm going straight up the y-axis because why not? Anything on the y-axis, we could even do, looks like 1, 2 is still in there. 1, 3 is in there. 1, 4, 1, 5. So I've listed a bunch. You can kind of see what we're doing, but nothing on the curve will work. And so let's test one of those values and see why it doesn't work. Let's test 1, 1. That's an easy one. So we're plugging in 1, 1 to both inequalities, and we want to see if it fits both inequalities. So in the first one, y is greater than x squared, question mark, because we're testing it. 1 is greater than 1. Is that a true statement? Is 1 bigger than 1? No. So it's automatically out. We can automatically throw the point out because it doesn't fit the first inequality. But we can go ahead and test the next one if we want. I mean, it's already out, but I can show you. So we'll throw it in the second inequality. All right, so it does work for the second inequality, but since it doesn't work for both inequalities, then we cannot use it as a solution. All right, that's all I have for this lesson. I hope you enjoyed it. If you have any questions or need any help, please let me know, and I'd be happy to be there for you.